Well, good evening, everybody. It's my pleasure to meet you. My name is Dave Hoelzer. I'm up here in New York right now. We're in the middle of a heck of a storm right now, so we'll see, make sure we don't have any electrical problems. At least I hope we don't have any electrical problems during this. And I'm going to talk to you a little bit this evening about some machine learning stuff. And before we get started, I just want to take a minute and explain a little bit about what our presentation is about tonight, what it's motivated by, and why I'm choosing to do this tonight. Personally, I think it's really awesome that SANS has not only reacted to the situation that we're all in right now, and particularly those students who were planning to be attending live conferences in the next month or two, but also just opening up all of this free stuff for folks. And know that I think it's so important. I mean, we, the faculty who are doing these, we're not being compensated for this either. It's just something we can do to kind of give back and help people take their minds off of all the bad things that are going on. And I'm sure that some of you have some really serious things happening. I know for me, we have a really good friend and business partner in the United Kingdom. He himself is sick, his wife is sick, and is now in an emergency room, unresponsive. So it is a terrible time for all of us. But let's just take a little while, about an hour, hour and a half, and kind of take our mind off of all of that, learn a little bit about machine learning and something really special that we have that's coming out in the next month or two. Now, as I go into this, I want to explain what this talk will do and what it won't do, and maybe help some of you to decide that this might be a talk you want to skip. For example, if you are someone who is already engaged in machine learning research and you have a good deal of knowledge about it, you probably are not interested in this talk. This is going to be very high level, very fast, and it's just enough to introduce all of the major terms so that someone who doesn't have a lot of familiarity can have a conversation, an intelligent conversation, maybe with a vendor, maybe with their boss or someone who's looking to procure something, so that you can decide whether or not machine learning is a good fit for you. So that's part of what we're doing, but there's more. Now, for those of you who are listening to that and saying, no, I'm not a machine learning researcher, I'd like to maybe learn some of this. Part of what we're hoping we're going to get out of this is the fundamentals of what this actually is, what AI and what machine learning is. Because if you haven't noticed, pretty much every vendor out there is telling you that they have an AI solution and does machine learning and it's just great. Now, of course, vendors have made this same promise for a very long time, and I myself have a great deal of concern about that in this particular space, as do data scientists in general. I was having a conversation with a couple of people on Reddit earlier today because someone just published a paper about some AI thing they've created that solves COVID-19. It's going to cure it. And in fact, it doesn't do anything like that. They've taken someone's code, made a couple of little adjustments, and it's not doing anything meaningful at all. But because AI and machine learning are so much the buzzwords of what everyone is trying to sell you and what everyone's telling you you need, then if it has machine learning or AI on it, people are interested, people want to sign up, people want to buy it. Now there's risk there, not just the risk of the thing didn't work. I think there's a much bigger risk, and the AI community, the machine learning community has suffered through this many times over the past decades because, for instance, even some of the techniques we're going to discuss tonight were very well understood in the 80s and 90s. We just didn't have computer systems we could do it with, but all of the math was done. And the evolution of the computers that we can do this with have been primarily driven not by machine learning research, but instead by graphics processing units and their application and the strong desire in the consumer market for gaming. And as those things have advanced, it turns out that those same devices are incredibly powerful for doing machine learning. And we'll talk a little bit about why that is. So one of those big things we're trying to get you to come away with is, what do these terms actually mean? How does it actually work? And that fear I was mentioning is that because of all of the overhyping, now, it might be too soon for me to say that, but as we work through a little bit of this, there should be some intuitive kind of aha moments as we go through it. And I'm hoping that at least a few of you are going to say, oh my goodness, is that all this is? Maybe it's not really where it needs to be yet. That doesn't mean it's not useful. we're actually going to continue through, and at the end, we're going to show you a really practical application of something you can do in real time today using machine learning and information security. So I hope you'll find that useful. And that's actually something I've kind of stolen out of our 503 class, part of what we're going to wrap up with. And it's also something that's talked about in that new AI or machine learning class that we're working on right now. And that's not going to be at conferences. That's just going to be done as a web series. And that'll be available sometime in May or June. But anyway, our fear is that because of the overhyping, we're going to see that another AI winter sets in, another drought, because all of the funding will dry up when all of a sudden the whole industry realizes everything has been overpromised. Okay, so I've said a lot in there. I do see that my friend Andy is saying that I've got the wrong screen up here. So if, Andy, if you're not looking at, I'm sorry, Dave, I can't do that, Adventures in Machine Learning, do let me know. As far as I know, you should be looking at a Jupyter Lab page. So if that's not the case, someone do let me know. You can, of course, put things over in the chat. I've got it up here on my screen, so I'm trying to pay attention to that. And oh, great, I see some people saying that that's the right screen. Thank you very much. I took off my bad artwork early. I was actually thinking about renaming this Adventures in Machine Learning and Bad Artwork. So I'll just throw that up there for a second. So that's my freehand HAL 9000. In any event, we'll be back to that a little bit later and have a couple little drawings I'm going to do with you. Let's get started because I only have about 60 to 90 minutes here and we have a lot of ground to cover. As we cover that ground, I am definitely going to be doing some hand wavy stuff. And that is most especially around the Python code, because all of this stuff, as you can see here, I'm using a thing called Jupyter Lab, which is kind of the newer iteration of Jupyter Notebook. And this talk tonight is not about the Python. I'll point out a couple of things about it. If you're curious about it or want to see some of the excerpts of it, you can get in touch with me. I'd be happy to share that with you. But I want to talk about the terms and how this works so we understand it and give you a practical application and some really strong intuitions about it. With regard to that, there will be some math involved. You're not going to have to solve any math problems. And I have tried very, very hard, both in this presentation, in the 503 class where we have this right now, and additionally, in the new webcast series that we're doing, to make sure that this is very accessible, meaning that you do not need to have an understanding of advanced mathematics. And what I'm calling advanced mathematics is really from the perspective of someone who is not a mathematician. Because if you are a mathematician, the math that's involved in this is actually not advanced mathematics at all. It's actually rather fundamental mathematics. But if you're someone who's perhaps may only taken high school mathematics or maybe taken calculus or calculus 2, this can look like or seem like advanced mathematics. Anyway, let's get started. I do see that Vijay is asking if this is going to be available. This will be available in some form, but I'm not planning on publishing this notebook until we release the class. Now, if you're someone who is taking 503, you actually will have some of the scripts that are at the very end. They're already available in that class. And you can get some of that out of the Show Me the Packets repository. I'll just put the name there. I'm not going to go look up the whole link. Show Me the Packets repository, which is out on GitHub. Not everything is there, but many of the pieces necessary to make this happen are there. Alrighty, so we're going to get started with this and we're going to introduce this idea of machine learning. And by the way, we're not using slides. I'm sort of on a campaign to outlaw slides as much as I can. So we're just going to use this Jupyter Notebook. For our machine learning, we're going to start with a problem that doesn't sound like machine learning at all. We're going to start with a topic called linear regression, which already, especially for me, it's 8:30 here, so I'm well past my bedtime. Linear regression does not sound like something that's not a math topic. It is, but it is not a hard math topic. One of the things you're going to find as we go through this and introduce and explain some of these terms is that much of what's happening in these terms is simply trying to assign a precise term to something, which can sound really hard if you don't use that term every day, but it's actually a very simple term. For example, linear regression. Linear is just a line. Regression Regression is a pretty easy term as well. Regression is really about the idea the idea of fitting. Now, I want to illustrate that for just a second. So let me just pull over to my my iPad here. Just give me a second to get the right page up. And let's use this one here. And this is just a rough drawing of some data that we're going to be looking at in a couple of minutes. And just to explain what's happening here in this graph, we've got some data, and I'm going to say that this comes out of a NetFlow repository within an organization. And what it's showing us is over time, how many bytes are being transferred across the network. This is the kind of thing, the raw data that you would be producing out of MRTG reports and other kind of utilization reports and creating charts and graphs of. Here, we're just looking at it as raw data and showing some histogram data. So we're saying that at this hour over here, we ended up with this number of bytes. So that's all that's happening in this graph. Now, when we look across this graph, you can see that over time, the data is not, it's not a straight line. And that's okay. Right now we're talking about linear regression, which I said regression is about that word fitting, and we know linear is about lines. So here's what that means. I'll give you a very simple definition. And for those of you who have more math training than others, don't be overly precise. Please allow me to be a little bit loose about how I define some of these terms tonight. But I'm going to say linear regression will simply be, can we look at this data and could you and I perhaps draw a line that best approximates what's happening in that data? That is a linear regression. Well, not exactly. I mean, there's an algorithm involved. Well, right now I'm just eyeballing that. The algorithm that's involved is we would need to be a bit more precise. For instance, if we were to pick a point, like I'll pick this point right here, this little orange point, and you can see that my line is rather far away from this point up here, which is the point happening at that time slot. So my prediction, my line is wrong. I made a mistake. It's an error. In fact, there's an error function that we could assign to this. We could decide, I'm going to figure out how far away from the line all of the points are. So I'm just going to make up some numbers here. Let's say that the first point is 2 below, and the second point is 2 above, and the third point is 4 below, and the next point is 6 above, and the next point is 8 above, and the next point is 10 below. And we did that for everything. I could add all of those up, and it would give me the total error. Although you may already see an intuition that's telling you there's something going to go a little wrong here, because if I add all those up, so the -2 and the +2, those kind of cancel out. Let me just ignore those. -4 plus 6, so we're currently at +2 plus 8. That's going to be 10 minus 10. So the overall loss is 0, which seems to imply this line is perfect. It exactly represents the data. It fits the data. But clearly that's not the case. It is very far away from a lot of the data. So there's a different way we tend to do this. We do a different thing called a mean squared error, where we take each error, so my first one was -2, and we square that. So that would be 4. My next error was 2, that would be 4. My next error was 6, that's 36. But by using the square, we preserve its magnitude. We actually make it bigger, but we preserve its magnitude. And if we add that all up, we now have a much better approximation of how wrong this line is. All right, so let's move away from the math. I know you might already be thinking that feels like more math than I'd like to do. I'm with you. Let me just get my notebook back up here. So what we're working with, though, is this idea of the formula of a line, which is really the only math you need to understand or know before coming into this. And I feel like that's pretty rudimentary. That's maybe 9th or 10th grade in the United States. Y is equal to m, which we usually define as the slope, times the x coordinate plus b, which we define as the y-intercept, the formula of a line. That formula turns out to be important because what we're going to do is ask the computer to figure this out for us. And it's going to use an algorithm that tries to minimize the mean squared error. So if it can get that error as small as possible, that means that is the very best line that fits that data. To get started, I've got some Python stuff here that's going to read in some flow stats I've got, which is, as I've said to you, hours with number of bytes that have gone by. Now, just as an artifact of the data collection process that this comes from, I end up with this third column over here that doesn't really exist. The data is really just the hour and the bytes, but I didn't want to massage it too much. I wanted to give it to you just as it is. So I just need to get rid of that column. Now, I'm going to tell you something now, and I think you will appreciate this much more as we go through the actual machine learning pieces. The majority of your time and effort in creating machine learning solutions is spent processing and cleaning your data. That's it. It turns out that actually building the neural network that's going to do the predictions for us is seconds or minutes worth of work, especially using the process we're using here. I am using a more simple kind of approach to it, a really nice interface to it. Though if you want low-level access to do that, you can spend a lot more time actually writing custom ways to classify data. But still, it's the cleaning and processing or pre-processing of the data that takes the time. Now, this is not a lot of pre-processing I need to do. I just need to make this column go away. So I've got some Python magic here. Don't let it distract you what's happening in there, this axis and stuff. But all that it's really done is it has chopped off that column. That's it. So I now have 112 rows of 2 columns. Column number 1 is the hour. Column number 2, it's marked as flows, but it's the number of bytes. Now I'm going to also make another little thing here. It's a super common practice that when you're trying to predict something with your data, you'd like to hold back some of your data, holdout data, we can actually even call it that, holdout data, that we're not going to train our machine on. Instead, we're going to use some of the data for the training, and then I can use the other data to see how well a computer does at predicting the rest of the data. Now, I'm going to just give you a little foregleam here. It's not going to do a great job at this prediction, but that's okay. There's a totally different intuition that we're looking for you to get out of this. We're going to move into some machine learning that has some really good outputs in just a few minutes. But now that I've pulled that data aside and I've created a thing called bytes that's got the first 60 rows, and then I've got one called all bytes that has all of the data because we want to do some comparisons and see how this does over time. This is just showing that, in fact, I have loaded that in, and it's printing the data out for us in scientific notation. It's just the default exponentiation that Python is going to do when it prints stuff out. And as I said to you, we are going to avoid talking about all the Python stuff. So I've got a whole big Python function here that we're just going to wave our hands and say, this Python magic is going to create some really handy functions for us that will allow us to plot things on the screen. That's it. Now, if you're interested in the details of that, I will just leave it on the screen for just a moment. You could come back and maybe snapshot that, or you can get it out of the notebook when it becomes available. But this is just allowing me to graph data out. That's it. And here's the data. And that kind of looks familiar. That's something like what my little drawing looked like. We can see bytes over time. And what we'd like to do then is ask the computer to try to fit that or do an approximation of the data, because we said that regression idea. Now, I just drew a line. All I did was approximate it by eye, but a regression is actually doing an algorithm. It's iteratively looking at a line compared to the data and figuring out what the loss is, the loss or the error, to see if it can come up with the best fit. That's what a linear regression is. Now, to make that work, I'm going to just create this error function, And this Python here, because we're not reading Python, so I'll just translate it for you, that is implementing the thing I described, a mean squared error. What I actually did to you was a sum of the squared error. We would just have to divide that by the total number of elements, which is exactly what this is doing. So it's a mean squared error is what we're coming up with. Actually, I'm just noticing I forgot to divide it by the number of elements, but I'm just going to leave it as is. It's going to give us a raw error score, and that's totally fine. Next, look at that. I'm done. The machine learning has happened. I know it doesn't feel like a lot happened. Here's what's going on. I have called a function that NumPy is just a mathematical library for Python, provides called polyfit. The polyfit allows me to try to fit a curve or a function to data, which is exactly what regression is. Since I'm talking about linear regression, that would be a first order function. In other words, the highest power found in there would be the power 1. Where did that come from? If you remember, at some point in your high school career, you dealt with things like polynomials, where you had x squared plus 2x minus 4. And that would be a second degree equation or a second order equation because we had x squared, the highest power. If we have y equals mx plus b, a line, the power is 1, x to the first. We don't write it because it's x to the first, but it's a first order equation. And what I've done here is I've said, please do a polyfit for a first order equation, trying to find the terms that would best fit that function. And when I do that, it returns to me 2 values. The values that it is returning to me here are effectively the m value and the b value from y equals mx plus b. So in other words, this function here is what we end up with. It has figured out that that is the best fit. So now wait a minute, this is very important. Machine learning, I said that machine learning is all about trying to algorithmically or programmatically minimize an error function. And I want to be clear that the kind of learning that I'm talking about tonight is very specifically supervised learning. Supervised learning is an approach toward machine learning where I'm usually trying to classify things or I'm trying to come up with some kind of a value. And I'll define the difference between a regression and a classification in a little while because there is an important distinction there. But effectively, I'm trying to make a prediction about something and I have some known data that I'm trying to work out rules for or trying to work out a function for. Having that known data and training against it is more than anything what defines something as supervised learning. In other words, what I'm doing is feeding in data and feeding in outcomes, what the answer should be, and asking the computer to work out what are the rules to make that happen. And that was a fundamental change that happened in machine learning in the 90s and going into the early 2000s. Because if you remember the 1990s and you were working in information technology, you are likely familiar with expert systems. And in expert systems, you spent, not the computer, you spent a lot of time writing rules for the computer to help the computer take the input and turn it into the proper output. That all changed. It all got turned on its head as we moved into this model, the most common model that we use today, where we feed in predictions, outcomes, with inputs and ask the computer to work out what the rules are, which is exactly what linear regression is. I plug in data points, I ask it, figure out what the coefficients should be for a linear function that approximates that data, that best fits that data, or minimizes the error. If I look at this one, it tells me that the error, well, this error doesn't look so good. 1.3 times 10 to the 16th. My goodness, we are very far off of the error. And again, I did forget to divide by the number of elements there. Do I want to bother with that? No, I'm not going to bother with that, but we could. It would not be difficult to do. But it makes it look like it's a huge raw error, and it is. But if we plot it out, it turns out that that our graph is actually not very far from what I drew. So our gut intuition was just draw a line there and that's about the best you can do. That was a pretty good guess. But could we be better? So far, what we should know is that machine learning is about fitting the data or creating a function that best fits the data. What we're doing is feeding in known data with known outcomes to see if it can work out a formula or some function that minimizes the error and that we can then make predictions with. That is effectively what's happening. So maybe there's a way that we could get a better approximation of this data. And I want to introduce an idea about that because there's another important intuition that we can get out of this. If you took calculus, now don't worry, we're not going to do any, but if you took calculus, one of the major topics in calculus is sequences and series. And unfortunately, the way it's taught is really not very intuitive. It doesn't help you to understand how it solves problems. But in the sequences and series section of your calculus class, what I'm about to say might actually explain a lot of what you were trying to be taught in that section that perhaps you didn't understand. The idea behind an infinite series, in particular, I have in mind a thing called the Taylor series, which is an infinite series that can be used to approximate the value of sine. Now, sine, you might be familiar with that. It's a trigonometric function, and it's a bit more difficult to create a linear regression on this one, because if we were to try to create a linear regression, the answer would be a straight line, but you can see that most of the time, that line is really wrong. This function, however, is a very difficult thing to try to kind of quantify. Now, it's easy to calculate, it's easy to talk to in terms of relationships of angles, but how do you write it as a function? Sure, I can write sine of 30 degrees, but that's not what I want. I want something like, x squared divided by 32 plus 15, that's going to give me the sine. And that's where the idea of a Taylor series comes in, or an infinite series. It turns out that we can create a prediction, we can create a function that could very, very easily and very accurately predict this one point right up here at 7.5. We could do that. And if we added a couple of terms to that, we could also predict some of the values a little bit to the left and a little bit to the right. And if we added more terms to that, we could predict further left and further right. And the more terms we add, the more to the left or the right we can predict. In fact, if we were to create an infinite number of terms, the Taylor series would produce a curve that looks exactly like sine. But just because we say it's an infinite series doesn't mean that we have to go to infinity. That's what a Taylor series is designed to do. But the way you use that kind of thing is you say to yourself, how accurate does this need to be? To how many decimal places, let's say. And then based on that, you work out how many terms you actually need to calculate. So even though it's an infinite series, as long as you are fairly close to the data or the point around which you're doing your prediction, you might only have to calculate 2, 3, 4 terms out of that infinite series. That's very tractable. So let's see if we can take that idea that maybe making this a higher order equation. Right now we did a first order equation. What if we tried to do it as a second order equation, a polynomial, or maybe a third order polynomial with a third power, or let's go for broke, a 15th power. And if I just try those, I'll have it do the fitting for those. It tells me that the first one, the first order, that was 1.3 times 10 to the 16th. That's how far off it is. The second order is 1.0 times 10 to the 16th. That's better. The next one is even better. And look at that, the 15th order is even better. It's still far off, but it's even better. So that makes it seem that more terms must be better. Higher order equations must be better. And if we graph this out, note what we get. Here's our straight line. That's our first order equation. And then this curve here is the second order equation. And certainly, as we go here from 30 to 40 to 50 to 60, it is definitely a better approximation of our data than what we see happening with our straight line. However, to the left, we do have to admit that at numbers less than 10, at values less than 10, it actually seems to be heading in the wrong direction. Let's try adding another term to that. Let's make it a third order equation. If 2 is good, 3 must be better. And when we do that, oh wow, so it is now low less than 5. It comes up and then it seems to be tracking better than the second order equation. This looks great. What we're doing is just manipulating the values to see, can I better fit this? One of the ways that this applies, and it's not directly the same, but it's analogous. We're going to go through doing some training with 2 different machine learning strategies. We're going to start them very, very soon. But when we do that, one of the things we have to do is figure out how many epochs, how many times should we run the training data through? More must be better, right? And similarly, more neurons must be better, all kinds of things, more must be better. But is that always the case? Now, let me just see, I can't read this. So yeah, you're right where I'm saying, Mark, why not just use 1,000? Now, I'll be honest, if I use 1,000, Python's gonna start to complain. So let me just try that. I'll change this guy to 1,000. And you can see, whoa, Python gets kind of upset by that. It does not want to do that. That is not a valid value for it. It's just too large. You'll in fact see it starting complaining much earlier than that. Like here, it's saying, I cannot properly fit that just because the numbers are getting too large. Something to the 40th power is just too much for it to handle. Let me go back to the 15th power. And yeah, I see my friend Eric is saying, perfect is the enemy of good enough. And that's exactly what's happening here. So let me just recompute these now that I changed that. And let's just scroll down. We have this, the second order, there's the third order, it looks better, but here's the 15th order equation. This doesn't look so good. In fact, what we've done is we have just done something like overfitting or overtraining. Overfitting. And that can be a difficult concept to get, but this illustration to me really makes clear what's happening. You can see that we kind of start off okay, but the longer we go, the more out of control this gets. When I was looking at the second and the third order equation, they were tracking with the data. In a very real sense, you could say they were kind of standing back and trying to globalize what was happening. They were looking at the overall curve, the overall data. But when you look at the 15th order equation, it no longer looks like it's really looking at the big picture. Instead, it's as though it's so fixed on trying to make it to this point and make it to this point and make it to this point and make it to this point. It's so fixated on that that it can no longer see the whole curve. In other words, we're missing the big picture because it is so focused on the individual details of what's going on. You've heard the expression, you can't see the forest for the trees. That is effectively what's happening here. And there's 2 ways that that can go wrongly. It could be that we are overfitting. That could have to do with how we are actually creating our model. How many neurons, for instance, if I am trying to deal with something that deals with, 120 bits of stuff, and I create 1,000 neurons to handle that, I am going to way overfit on that, which means that there's no need for the network to learn anything. It can just remember every bit from every example. But the other way we can use this idea or this picture here is this idea of overtraining. Overtraining is my network or my machine learning algorithm becomes so good at spotting the training data, like what this is doing. It's dashing from point to point, that it has no hope of doing any useful predictions in the real world. And in fact, let's just prove that true. Here, I'm now plotting out all of the data. Remember, I had set aside some of the data so that we were only looking at a small section of it for our initial training, but there was a much larger range of data so we could evaluate predictions. And it's kind of interesting. This data turns out to be cyclical, and that's very common for network data, where we have some spikes, but then we dip back down. And as odd as it is, that line turns out to be a much better approximation than what's happening in the second order equation, and certainly in the third order, and absolutely in the 15th order, which is so far off the charts you can't even see the real data down here anymore because it has totally overtrained or overfit on that data. So let me just pause for a second. Linear regression is not the point of this. The point here is what we've taken away so far. We can say that machine learning is simply using some algorithm, and don't worry about how the algorithm works. That's not important for us right now, but it's using some algorithm that automatically adjusts coefficients in a function in order to best fit the data. That allows us to make predictions. The way it makes those adjustments, so how does it decide, if it's wrong, is it's measuring the loss, which we said is the error. It's the amount off you are. That makes total sense. We can even imagine ourselves solving a problem that way and trying to see, well, how far off am I? Let me make a little adjustment here, a little adjustment there. And if you think about this in terms of maybe measuring something physical, like you're trying to fit something into a space, you're making a piece of trim to go around your window. So you probably have been taught the saying at some point, measure twice, cut once. Even then, when you make that cut, it's always better to make it a little bit too big because you can always make it smaller and adjust and adjust. And you know it's too big because it doesn't quite fit, it kind of overlaps. Here, we're looking at it mathematically. Oh, it's a little too big, so I need to make it smaller. Oh, it's a little too small, I need to make it bigger. So we can look at those numbers, look at the error, and see which way does it need to be nudged. The computer is doing that as well. It's looking at the slope of that error. It's saying, is the error going up or is the error going down? If it's going up, well, then I need to make the number smaller. If it's going down, then I'm going in the right direction. Keep going that way. So that's all that's happening. That loss is the same as the error, that term. That's all it means, but it's all the same stuff. It is really saying how far away from reality are we? And there's another term you'll see here. It's used in data science. It's used in statistics and machine learning, ground truth. Reality and ground truth are the same thing. Facts, not alternative facts, ground truth or facts, things you can actually measure. All right, so then let's turn this into real machine learning because linear regression is machine learning, but it's not what most people would think of as artificial intelligence or machine learning. In fact, though, even just take a pause and think about that. If you polled most of the people in your enterprise, particularly the people who want to buy or spend money on, or even the salespeople who are telling you to buy machine learning and AI solutions, is that what they think it is? Or do they have a totally different mental picture about what AI is? We are totally overselling and overhyping what AI does today. But that doesn't mean that it doesn't have value. So let's look at another example of that. We're going to take a quick stroll through kind of the hello world of machine learning. And the problem we're working with is a thing called binary classification. You'll also find this called sentiment analysis. That's the same thing. Binary classification means I'm trying to see if it's one thing or the other. It's two different things. This is being called sentiment classification as well, because that's what the original problem was that was proposed. Can you look at a movie review, and based on that, can you create some algorithm, some process that will learn to identify the sentiment? Is it positive or is it negative? That's all this is doing. Now, the problem we're going to work with here, I know is not an information security problem, but we're going to take some of the fundamentals we learned here and turn it into a much more important problem. Where we are identifying unknown protocols passing on a network in real time. And to me, that's a valuable problem. So we'll just introduce it with this here. The idea here is we've got movie reviews that IMDb generously donated to the world. And in these movie reviews, there are 25,000 movie reviews that are designed to be used for training and 25,000 that can be used for validation to see how well you did. This problem, as we work through it, is probably going to seem pretty easy, But know that less than 10 years ago, this was a cutting edge problem. And the solution that we work out with here would have been a prize winning solution just 10 years ago for this problem. But machine learning has definitely made tremendous advances, and there are far better things that we can do than what I'm going to demonstrate here. Why am I demonstrating this then? Why am I using something not optimal? Because there's some important takeaways I have for you that are related to what machine learning and AI is actually capable of before we turn that into a practical information security problem. Now, I want to explain the structure of this data a little bit because it will explain some of what's happening inside of this notebook. We've got the movie reviews and we've got the labels. And fortunately, someone has already done a great deal of work massaging this data because these are words, but we've already seen that really this is adjusting coefficients and functions, and words don't really fit well in functions. So how can we make those two things work together? Well, what someone has already done is taken all of the reviews and they have encoded them. The way they've encoded them is they have taken all of the words that are used in all of the reviews and they performed some frequency analysis on that. The word that appears the most frequently is listed as the first word in the data set. The word that occurs least frequently is the very last word in the data set. Why they've done that, I'll explain to you in a few minutes. It'll become obvious why that was a good choice. But then, because they've created these indices, these numbers that associate with the words with this table, with this dictionary, it means that if we had a sentence like, the quick brown fox jumps over the lazy dog, and the way the index worked was, the was most common, fox was second most common, brown is third, is fourth, quick is fifth, well then this review would be encoded as 15327111168. The, quick, brown, fox. So the numbers represent which word we've used. That still might seem a little bit strange to you. There's a really good reason we've done it, and it's this part right here. I'm about to load this training set in, and I don't know if you can hear fan noise where I am. I've got a big beefy machine that we use here that's got a couple of GPUs in it and oodles of memory and disk space where we do all of our machine learning research and that kind of stuff because you need a lot of memory and GPUs really make the training much, much faster. And in loading this in, I've told it to use the most frequent 10,000 words that appear in that data set. 10,000 words. Now there are far more words. I seem to remember that there are 83,000 words in that total dictionary, but that would mean that I would need to keep all 83,000 words in memory at the same time, which doesn't sound bad, but let's make that more difficult. I need to keep in memory 25,000 rows of data that are 83,000 columns wide. That is a lot of memory. So to make that simpler, I'm just going to use 10,000 words. And it turns out you don't need all 83,000 words to do a pretty good approximation of what's happening. So here we have a little bit of Python magic. It loads in that IMDb data. And here it's just showing me what that data looks like. So I've got the very first review. There it is, 1/14/22/16. And as we know, that represents the words. Inside of there, I've got a training label of 1, which I seem to remember 1 is a positive review and 0 is a negative review. And then I've just got some examples of some words. So you can see fawn is word 34701. Zucchino is 52006. Just a couple of random words there. This is nice for the computer, but we'd like it to be readable for us. So I've got a little function here that is going to turn that into something that you and I can read. And I've also written a little function here that's going to tell us whether or not it's a positive or negative review. Again, I don't want to read the Python with you, but you can see here we have taken that review and turned it into text. Now, I just want to explain that in this text, you'll see there are question marks. The question marks indicate that the word that was in that place is not in the index that I have loaded. Remember, that's an 83,000 word dictionary, but I've only loaded the first 10,000 words. So there are some words that it doesn't populate. Even so, let's see, it says this is positive. That's how it's been pre-classified. That's the training label it has. It says, this film was just brilliant. Casting, location, scenery, story, direction. Everyone's really suited to the part. This does sound positive. All the punctuation is gone. That's just an artifact of how the data has been manipulated. But we can reconstitute these. They're sort of freeze-dried, but we can pull them back together. Let's just take a second. What we need to do, though, is turn this into something that I can push into math. Push into math. And to do that, I need to make it something that's easy to manipulate. So I'm going to, for a second here, I'm going to pull up my iPad again. I want to take a stab at explaining something, and I'm going to try to make this really simple. There's a field of mathematics that we primarily use when it comes to machine learning. There are a whole bunch of things that are used. I mean, we are using calculus and partial differentials. There's a lot of that happening. But the majority of what's happening in machine learning is actually making use of linear algebra. And linear algebra sounds a lot like it has to do with lines, like the algebra of lines, which is not really true. It's really, at its most fundamental, it is really about transforming things from one space to another. And the way we represent things, for instance, if I gave you a coordinate, so if I gave you a coordinate like 1, 2, 3, put that in parentheses, that coordinate, there's another way I could write that. I could also write it in row major form as 1, 2, 3. Don't worry about row major, or as column major form. Again, don't worry about that. 1, 2, 3, which for some of you with maybe a physics background or other kinds of education, you'd look at these and say, oh, that's not a coordinate. Those are vectors. And I know that many have been taught, especially in physics, that a vector is something that has both magnitude and direction. And that is true in physics, but the mathematics definition is not that restrictive. In fact, if you look at the definition even in a physics book, what you'll see is that a vector is something that has, and it will say something along these lines, a vector is something that has both magnitude and direction, comma, for example, because there are many other things that make up a vector. For instance, this right here, these 3 coordinates, that is a vector, but written as coordinates. Here it is written as a vector as a row. Here it is as a vector as a column. I have over here, you might be kind of looking at what's going on back here. You can see I've got this, this attempt at a 3D cube sitting out there on those 3D axes. If you wanted to draw that on a piece of paper though, or you wanted to draw it on a computer screen, you would have to do some kind of a translation. Because a cube, like a Rubik's Cube, that is a 3D thing, but your computer screen is flat. So you need to translate it from that 3-dimensional space down to a 2-dimensional space. And it turns out that we can use linear algebra, which is, forget lines, linear algebra is the algebra of vectors. It is the manipulation of vectors, or let me make a more complex vector, or of matrices, which are vectors with multiple rows and columns, which you'll also find the word tensor around. I'm not going to go into the depths of what tensor really means, but we can, for ourselves, we can think of it as a matrix or even a matrix of matrices, groups of vectors. That's what a tensor is. And the main product, at least the one that I work with most often, and there are others, but it explains the naming of Google's product, TensorFlow. It's really about the mathematics of vectors and how we can manipulate them. And it allows me to take that 3D cube and to represent it in 2D space, which turns out to be a super simple thing. If you want to make it absolutely the simplest projection possible, all you do is you get rid of the Z coordinate, or however you choose to mark them. I almost always think of these as X, Y, and Z, and I know that I am not in the majority in that one, and a lot of people will label the up and down as Z. It's just kind of where I started. That's kind of how I ended up there. Anyway, so linear algebra is about translation. What does that have to do with machine learning? Why does it matter? Well, in order to use linear algebra, why do I want to use it at all? Because it turns out that your GPUs are phenomenal linear algebra systems. They are phenomenally good at doing parallel calculations on matrices. All that we do in computer graphics is based on linear algebra. So those devices are exceptionally fast at it. They're optimized for it. So we're going to leverage linear algebra. That's what the algorithms do. And there are some very specific rules. The only one that we really care about is that in order to leverage linear algebra to solve our problem, all of our vectors have to be the same shape. The same shape means same number of rows, same number of columns. Now in our case, each row is going to be a review. But a review, different reviews have different numbers of words. Some reviews will have 10 words, some reviews will have 80 words. How do I make them all the same shape? And if I were to arbitrarily say, let's make it 100 and we'll just pad out the ones that are too small, it doesn't matter what number you pick, you're either wasting a lot of memory or you will truncate reviews. So we're going to take a slightly different approach. What we're going to do is vectorize the data. Vectorize, well, we know what a vector is. It's an ordered group of numbers, an ordered list of numbers. I'm going to take the review, so here is the review we currently have, and I'm going to translate that into an ordered list of numbers into a vector of 10,000 columns. And that 10,000 might sound familiar because we loaded in 10,000 words. Do you remember that? So those 10,000 words, each one of those words is going to represent one column in our data. In other words, if word number 1 is present, there will be a 1 there. If word number 2 is present, there will be a 1 there. If word number 3 is not present, there will be a 0. In fact, if you look here, I've printed out the review as numbers here, but down here, I have printed out the vectorized form of that. Word number 1 does not appear in that review. Word number 2 does, word number 3 does, word number 10,000 does not. Now, fortunately, Python here is saying there's no way I'm printing out all 10,000 of those, so just take my word for it. It is now just marking every word that appears. It's not counting how many times that word appears. It is simply indicating that word is present. And there's a name for this approach. This is called the bag of words approach. So you can imagine you have a bag and you say, oh, the, I've got a the here, so I'm going to put a the in the bag. And you only put one copy of each word in the bag. But now all of our rows will be 10,000 columns wide. That means our vectors are the same size. With that done then, I am ready to do some training. And down here, I know it says a bit more data manipulation. I'm just doing a bit of manipulation here to pull out some validation data. Don't worry about that at all. But this part here is everything required to build this neural network. So not linear regression anymore, neural network. This is a deep learning neural network. That's it. And if I simply run that, so we have to give it a second here. Oh, off it goes. Look at that. It's telling us about the training. The magic has happened. In its first pass, it had an accuracy of 77% while training. After it finished that pass, it took the validation data and checked how well things were going, and it was up to 87%. It then started, so this was the average over the whole epoch or the whole iteration, the whole set of data. And then here, we now end up with an average of 90%. Wow, that's much, much better. So this 77.8 was average. This probably started at around 89 or 90%. But the validation accuracy is lower than that. It did go up, it was 87 and it's now 88. So that means that it is still learning, But why is the validation accuracy different? Well, remember, it's using the training data to actually adjust all of the coefficients to figure out how to best fit, how to minimize the error, the mapping, the translation. And actually, I'm going to give you a big idea here. I showed you a 3D cube, and I mapped that to a 2D space. So I want you to think about this a totally different way. What we're doing is creating a 10,000 dimensional vector that describes a movie review, and we are translating it through a function that maps it into a space of either positive or negative review. So we're translating the 10,000 coordinate system to a two-dimensional system, 10,000 dimensions to 2. And of course, none of us can think about what 10,000 dimensions look like. It's just mathematically abstract, but that's what's happening. So in the epoch, in the training data, it is working with that data to make those translations from 10,000 dimensions to just 2. And then it takes that holdout data, that validation data, and says, how well are we actually doing? And based on this 88%, it's going to feed back some information. It's not training on this, but it can feed that information through and make some more adjustments. So our next pass through, we're at 92%. We have improved slightly. We're now at 94% on the training data, and we've improved slightly. We might benefit from some additional training, but let's actually try it out. I am going to ask it to do predictions on all of the test data, and it's already done. It really is that fast. The thing that takes the time is the training. And in this case, the training did go quite quickly because I'm doing a demonstration and it's not a very complicated network. But if I wanted to make a much better prediction, I would need a better network, and I would use a slightly different approach. So the training would take a great deal more time. But still, once that network is trained, the predictions are very fast. Let's see how it did. The first one, it says it's predicting it as a negative review. Please give this one a miss. And the rest of the cast rendered terrible performances, and the show is flat, flat, flat. I don't need to read more. That sounds negative. This one, it says positive review. This film requires a lot of patience because it focuses on mood and character development, and the plot is very simple. Doesn't sound good so far, but let's keep going. And many of the scenes take place on the same set in France's, the Sandy Dennis character apartment, but the film builds. Okay, so it starts off kind of in the middle, but this does seem to be headed toward a positive review. This next one. Many animation buffs consider it the great forgotten classic, the genius of. This seems like a really long positive review. Positive review. I generally love this type of movie. However, now you can read further if you'd like to, but you and I, when we get to that word, however, we know this is taking a bad turn. And in fact, if you read all the way through this, this is not a positive review. It is 72% sure that's a positive review. It isn't. There's something important here, and this more than anything, I mean, we got to see some of the terms, we got to see the learning happen, and we discussed vectors. That's all very important stuff, some concepts we needed. But this review right here is the major reason that I use this as a demonstration. It is very, very easy to fall into the trap of feeling as though the computer understands what's happening. It absolutely does not. You and I, if we were trying to classify movie reviews and we found something that sounded good but then had the word however or the word but, we would know because of the nature of the English language that this is headed for a bad turn. The computer does not understand it. What's really happening here, I've heard termed by one mathematician, I really love it. I think she's absolutely right to call it this. This is more than anything an advance in computational statistics. What does that mean? Well, remember we have a bag of words. And what we've really worked out, what the computer has figured out, is a way that it can translate that 10,000 dimensional space down to the two-dimensional space for positive or negative. And based on that translation, it knows that if these words appear together in a review, 72%, this is positive. but it isn't in this case. So there is absolutely no understanding that's happening here. This is really just mathematics that are being applied to it. That actually leads to one of the things that you'll hear discussed if you work with some of the vendors. Let me just shut down this kernel. I'm going to switch over to another notebook here, because we want to move on to the real meat of this presentation. We want to apply this, which is what that web series is all about. And what we're doing in 503 now is we give you all of the basics, the fundamentals of how to do it. We teach you to build them, but it's about building things you can actually apply and go use rather than just the theory behind it. Because my experience has been that if you look at classes on machine learning, you are either looking at something that is more or less pure mathematics, which is not accessible if you're an engineer just trying to do it, or it goes way the other way, and it's someone who's saying, well, you just put this here and put this number there, but no explanation of why you use that number or how you come up with them. So instead, we're trying to make this a very, very practical applied machine learning. And one of the things that you walk away with is what we're going to talk about here. Anyway, I started to say that if you talk to vendors today who are using machine learning and AI solutions around malware, for instance, or around threats on networks, there's a huge market in that. If you really push on them, they'll explain that, well, sure, what happens is, it's going to classify things, and in real time, it's going to create an alert. And if you ask, well, tell me, what happens if it doesn't know what it is? They'll tell you, well, okay, then it goes to the cloud for additional analysis, which sounds amazing. The cloud, there's the marketing term from 10 years ago, right? We send it to the cloud for additional analysis, which perhaps gives you visions of massive data centers full of GPUs grinding with AI to figure out what this is. But that's not what happens. What happens is it's sent to a human being who looks at it and says, oh, that's good or that's bad. Which to me, I understand the practicalities of that because you're trying to market a service and sell it and make it work. But it means that when your machine learning fails, you just fall back on the human to tell you if it's good or bad, which to me is no longer machine learning. And honestly, if companies realize that many of the products they're paying for machine learning, in the end, if it can't figure it out, it's just an analyst pushing a button, they might feel a little bit disturbed about the money they're spending on it. And I don't want you to think that they're all like that. There are some quite good products out there. IBM has created some really good training data and some models that are not public domain. They do not release any of this, but do a wonderful job for doing device identification, identifying things that are out of profile. But it's quite expensive. What can you do on your own? What can you do without having massive amounts of data? And what can you do in real time? That's where I really care about. And that's what we're going to look at here. So the problem we're going to try to look at, and that's what this notebook is talking about, is we are going to try to look at network data that is passing by. And we're going to see if our network can identify what protocol is contained inside of that. And I want to be clear here. I'm not talking about, is it IP or is it TCP or UDP? I mean, is it DNS? Is it SMTP? Is it SSH? Is it TLS? I'm looking only at the application layer. Our network is not going to look at the ports. It's not going to look if it's IP or TCP. It doesn't care if it's IP or IP version 6. It just doesn't care. It only is looking at application or payload data. And my theory in putting this together initially was, I'll bet because application protocols all tend to have headers of some kind, I'll bet that there is some structure you can identify to find different protocols on your network, unknown protocols. And if we only looked at maybe the first 16 bytes, we could probably find protocols. So that's what we're going to apply here. And I'm not going to read all of this to you. This is talking about all of that. Part of what I'm doing in here is I'm going to pad out our data, because imagine we have a session that starts up and there are only 10 bytes of data sent in the entire session. I said I want to pull out the first 16 bytes, which helps me to find the size of my vector. And we know that's important because we said they all have to be the same size, because if they're not the same size, the math doesn't work. So I'm going to pad them out. If they're too small, we're just going to pad them out. And by saying first 13 bytes, here's what I'm actually going to get pulled out. What I'm getting sent to us, and we're going to see this integrated. It's not just this notebook. If you can stay till the end, what you're going to see is this in action in Zeek, running in real time. And Zeek, it turns out, I love Zeek. I use it for a lot of stuff. We do a lot of automation with Zeek. It's another thing we do in 503 a great deal of. Zeek is very, very reluctant to give you the binary data in any kind of way that you can send it somewhere else. So we kind of had to jump through some hoops here, and what we've done is gotten a Zeek script running that will fire us over the first 16 bytes as hexadecimal digits. They're all kind of mushed together here, so that's what we're seeing here. And this is what DNS request data looks like. Now, ultimately, I'm going to need to translate things in and out of that format because I'm going to be trying to run this in real time. And if I were just doing this as an experiment, I could make a much simpler notebook. I'm not going to read the function, but what this function does is allow me to pass in those bytes, and it will spit back to me a string of bits. Why a string of bits? Because machine learning, it turns out, especially the kind we're doing here, it uses weights to adjust the values in the neurons. And when it's doing that, it's using very, very small values to make adjustments to the learning. If I use a value like 65,000 in one of these fields, that is a huge value. And with a really tiny weight getting applied to that, it's going to make no difference. It would be like if you've taken physics, classical physics, one of the things that you know is true is that because of Newton's laws, when you jump and then you fall back to the Earth actually falls toward you as well. But when you work out the gravitation toward that, in the function that you would use to do that, you would have big G representing the gravity of the larger body, the Earth, and then little g, your gravitational constant. Your gravitational constant is so inconsequential next to the Earth that we can't even measure how much the Earth moves when you jump. And that would effectively be what was happening here if I use really big numbers like 65,000. That doesn't sound big, but in the order of the size of the weights, it's very large. So you typically want to make your vectors fall somewhere between -1 and 1. Most are going to try to scale those down to fit between 0 and 1. In fact, that's what we're going to do. We're going to use bits. They're automatically zeros and ones. But -1 to 1 is the typical range we tend to use. So all this function does is take in a hex string and spits out a bunch of bits. Here I'm just going to read in some data. I've got some data sitting in this content directory. Let me just poke in there for a second. And I think these are all going to be kind of large. Maybe the Kerberos one isn't too big. And I have done some pre-processing, pulling out just the first 16 bytes of a whole bunch of Kerberos response packets. That's all that's here. So I have labeled them. I have said, hey, these are Kerberos, but I've done nothing else to them. There is nothing marking up where what the header looks like or where the bits are or what things indicate what. None of that is done. But now that that's loaded in, I could take some data and have it spit that out as bits for me, which means we're just about ready to train this. In fact, I feel like I'd like to get to that. Let's move to that. I've got some stuff here that's going to read all of that in and build it into training data in memory. So it's going through everything that was in this directory here, all of these different contents, all of the different protocols that I have already extracted data for. So it should be able to understand all of these when we're done. And it loads all of those in as data. If we look at some of it, we can see what they look like. It's saying this is an SMTP response, and these are the bits that make that up. And then further down here, we can see what the actual size of that is. So with what I've loaded in here, I now have 64,000 rows of data. That's how big my training data is, made up of 129 different features. I use the word dimensions here, so I'm reluctant to use it again. It's a two-dimensional array. But when we are talking about our features, you will also find that in machine learning, we would say this is a 129-dimensional vector. In that vector, the very first column, though, is the label, what is it? And the rest of it is the actual features. So we actually have 128 features plus a label. So this Python magic here pulls all the labels off, and this Python magic pulls all the data out. So I now have two different arrays, one that has the labels, one that has the training data. With that done, I'm now going to pull out all of the labels, identify what our labels are, our classes, and we are now ready to build the network. And there's a lot of information here that can be read about how batches work and all that. None of that matters for us, however, because we want to see it work. Here is everything needed to make this thing work. That's it. Again, the pre-processing, the gathering of the data, that's where all of the work is. So as it goes, you can see we're already up at 98% here. At this point, I would start wondering if I am overfitting on my data. And I think we just passed that threshold, because you can see that my accuracy was going up. It was continuing to go up, but now my accuracy has gone down a little bit. And you may have noticed it did bump back down, but our loss was decreasing. While this was training, though, if you were paying attention, you may have seen that this number actually shot above this number. So somewhere between 3 and 4, I should be stopping this training. I am a little bit overtraining or a little bit overfitting, but that's okay. We're going to call that good enough, like Eric said. We don't want to make it perfect. I'm going to create a function here that lets me just do some evaluation of that with some Python magic, and then I'm going to pass it some data. Here I have DNS request data. None of this data was in any of the training data. And if I ask it to look at those, it properly identifies all of those as DNS requests. Here I have SSH connections. Again, none of these were in the training data, and it identifies all of these as SSH. Here I've got some web connections. It properly identifies all of those as web requests. This looks pretty promising. But we need to make a little bit of a modification to this, because here's the thing. What's really happening is this is computational statistics we set. What it's working out is the likelihood that it's any of those given categories. So I've asked it here to classify a piece of test data, and it's giving me the raw predictions. Now those look scary, so I'm just going to translate them into something that's a little more friendly, percentages. 99.999%, it's whatever category 0 is. And there's a really small possibility it's this one over here. So these are just probabilities. That's it. The way we've been pulling it out so far, when I was printing out what the result is by asking it for a thing called argmax, which is give me the field that has the highest value, the one with the greatest probability. But maybe there's a better way. Maybe rather than just seeing that raw number, maybe there's something else we can do. And I'll tell you where I'm heading. There is a very big problem in machine learning that we think we have a solution to. I don't think it's really that amazing, but it works very well. With supervised training, which is very much what this is, we need to have labels for everything that we can identify. It knows how to put things in those boxes, but it doesn't know how to find things that don't fit in those boxes. Now that is usually a problem that you deal with unsupervised learning, but that has a whole different problem. Now I do see that Stacy is just asking, how would it do if we had a tunneling protocol over DNS? Now if your tunneling protocol was over port 53, but not embedded inside of a DNS application layer, then we would absolutely light that up as being a different protocol. This will work. However, if you're talking about something like using, what's the name of that, iodine, where you're using an actual DNS application layer to tunnel things across, no, because that really is DNS. Could we better train this with more features to identify what normal DNS looks like and how things behave? Absolutely. So we could head toward the road of how could I be tunneling something deeper inside of an application layer? In any event, coming back to this here, unsupervised learning is what we would typically be doing to find things that are outliers. That has a whole set of problems all its own, and we're not going to get into that tonight because I think there's a simpler solution to this problem. Let me show you what our approach is to identifying things that we have not been able to classify. I have written a little function here that's returning not only what the name is, what it classified it as, and you can see that for all of the known data, things that it understands, it's coming up with a really high likelihood that it's HTTP or DNS, 99% sure. But over here, when I pass it things it doesn't know, it still sticks a label on that, but it is far less confident. Now I'm only printing out one of the values. Since this one's 34, there must be other percentages sprinkled around in the others, but I'm only printing out the highest one. And even this one here, HTTP, it says 85% likelihood. That's not very strong, not compared to these. When it's something it knows, it knows. So our idea is, well, let's stop trying to classify things in that way. Rather than worrying about how do I find things that are unknown, let's look at the strength of the prediction. Now, interestingly, I have started to see a couple of posts recently in the last month or two kind of talking about this technique that we're using. Again, it's not terribly revolutionary, but it works very, very well. You can see that for things it knows, and I'm using arbitrarily 98%, it says absolutely that's what it is. For things that are less than that, I'm saying I don't know what that is. But how do I turn that into production? How do I make that real time? Well, the time is spent in doing the training. And this is a simple model with simple data that we have here. But let's see if we can take this and turn this into something practical. So I'm going to switch over to a terminal here. And what you're looking at on the screen here is some output out of this. It is actually running in real time right now, or at least I think it is. Yes, it is. I'm actually going to stop it because we're going to retrain it in just a second. And it's showing me what it seems to be finding. And I currently have it reporting to me things that are at less than 95%. And it needs some more training around DNS. And I know that I actually know kind of what the problem is that's going on there. When we did the training for DNS, we did the training initially with DNS requests and DNS replies as separate things. And it turns out that they actually look a lot alike. So it has a really hard time with DNS right now. We're going to need to do a little retraining on that. But because we have some knowledge in the protocol space and a little bit of knowledge in the machine learning space, those two things together can help us to do better feature engineering to figure out how to better fit that data. In this case, rather than looking at requests and responses, let's just call it DNS. That's probably a much better approach. But you can see I've got some other things going on, like it's saying this is QTLS. What's that? That's a Google Quick UDP 443 with TLS. Now, it's actually not that. You can see it's a 67% possibility. It's not that. And looking at the port number, it's really clear that it's not that. Some of you might be able to recognize that. That's NetBIOS. So this is a NetBIOS broadcast. And yes, even today, with all Windows 10 and 2019 servers, you will still have NetBIOS broadcasts in your network, as horrific as that is. So can we train it to find those? Now, I hope, I have to be honest with you, I don't remember. I think that's the data I pulled out ahead of time. Let me just have a quick look here. DNS response, NetBIOS, I do. So you can see here, I previously, if I can manage to type here, I pulled out some NetBIOS data. And that NetBIOS data is coming out of a packet repository here that we have that's got a couple of terabytes of packet data in here. Not that I need terabytes to solve this problem, because in fact, when you look at the actual data I have, I'm only dealing with 430,000 bytes of data total. And what I have there is just packet data, but I also have a very useful script here called build classification Zeek data. So I have a little Zeek function here that is simply going to take the data and it is going to send me the first 16 bytes of data. In this case, since I'm dealing with DNS or UDP broadcasts that are being sent to port 138, that would mean things coming from the client to the server. That's exactly what I want. So I don't need to make this change. I've got some notes in here that if I were looking for a response, I would need to change this. And it's only UDP where I really need to mess with that. But anyway, with this function, all I need to do is run Zeek, reading in the packet capture, passing it that Zeek function, and I'm going to send the output of that into training data, and let's call this NetBIOS 138. That's just an arbitrary name. It happens to be the same name as what I have there for the packet capture, but it doesn't need to be that. And if I go in that training data directory, some of this will look familiar. There's actually more here than we had in the notebook. You see that we have QTLS in here. We've got HBB TV, which is what all your Samsung TVs are doing, Drobo stuff, DLNA, media clients, boot discovery, all kinds of other stuff. But all I need to do is take packets, figure out what it is, take some packets, run it through the script, generate this data. The data we have generated looks like this, but I don't need to look at any of that. The next step, I'm going to come back here and use Python against my training thing here. Where is it? Train on data. There we go. Off it goes. I've got a couple of legacy errors here because of a Python version I'm using. It's loading in all of the training data. Give it a second here. And the magical training is about to happen. Of course, it's going to make me a liar now that we're doing a live demonstration. I'll just talk while it's going. So after it completes the training up, finally, there it goes. So it figures out what all of the different protocols are because I believe in automation. So it automatically figures out all of the protocols that are now involved. It's working through all of the training. We're already up to 89% here. I have it running at 4 epochs. Once it's done, we'll just restart it. Wow, it's already at 99% and still kind of climbing. So it looks like we're still learning there. So it looks like 2 epochs is still okay. You can see the loss is decreasing. I do want to mention something I didn't mention before. If you take the same model with the same data and train it multiple times, there's an oddity you might run into that's very easy to understand. When you run it with the same data multiple times, you'll find that your accuracy and your loss are different. Why is that? Because when you build a neural network in this way, what it's doing is a process called gradient descent. That gradient descent is really using, there's another word to throw on there, stochastic gradient descent. Stochastic meaning random. It's actually selecting a whole mess of random values to use within the neurons. So it doesn't know what to use. It just puts in random stuff and then tries some data out and sees how it goes. Like with our data, when we were doing the linear regression, we could just draw a line and then measure it and see how it goes. Now we could approximate, we could just draw, but it can't do that. It can't see it. So it's just a guess, and it's not a very good guess. And that's why the accuracy starts out very low with a very high error rate. And it's then looking at, now remember I was talking about with linear regression earlier, I said it's looking at the slope of the error. Is the slope increasing or decreasing? That's how it figures out which way to go to make it better. Well, I used a different word here. I used gradient. Gradient is slope in 3 or more dimensions. So all it's doing is starting out with random values and then following the slope in more than 3 dimensions and descending toward hopefully a global minimum for the error function. It's trying to figure out how it can minimize the error. That's it. And you'll find that you end up with slightly different accuracies and validation and losses because these functions don't have to have more than one minimum. Some of them are global minimums, way low, but some of them might be like a local minimum. So it could actually find itself in one of these little valleys and settle there, but not actually get to the best possible value, because there's no way to look at the problem and know what the best value is. In fact, I'll tell you one more thing. Let me just get this running again. Classify. And I'm going to just switch over to where we can do some monitoring on this. And let that pull up. So there it is. It's already classifying data again and running in real time now. And whoa, I've got some other problem there. Oh no, it's not another problem. It just hadn't finished its messages. So one of the other questions people have, and we do not have the time for this tonight, I gave you a couple of networks there that I just put on the screen and had a certain number of layers with a certain number of neurons. And some of you might have been trying to write that down. Don't waste your time. There is no magic to that. There is no science to that. This is purely an empirical field. Another way to say that is experimental. Why does my network have 4 layers and why do those layers have these many neurons? Because I tried a whole bunch of other values and those values worked well. That's it. There's no science to it. You do develop some intuitions about what to do to make things better, but it is purely experimental. However, at this point, you can see it is up and running. There is currently no data passing by that it doesn't understand, which I guess is a little bit unfortunate because there's nothing to see. It's only going to show us stuff if it's less than 95% here. But it is now running in real time and classifying the data. For me, in doing managed security monitoring, this is incredibly valuable because I am super interested in knowing when there's something communicating on that network that I'm unaware of or I haven't seen before. If in learning a network and understanding what protocols are there, and of course I can take this same network because it's not IP address specific, it's only looking at content. I can take this same trained network, drop it on another network, and immediately begin to find things that it has never seen before. Finding outlier protocols allows me to find things that shouldn't be on our network. Now I do have maybe 3 more minutes here. Let me just run through here. I see a couple more questions came in here. We've got from Zaid, what's the best machine learning approach for Microsoft anomalies? There is no best. It is really experimental. I personally am finding a great deal of success in using deep learning neural networks and convolutional neural networks. Convolutional neural networks, if you do some reading on this, you'll find are primarily used in the field of image and video recognition. However, they turn out to have some really wonderful applications in log analysis and other kinds of data analysis. So we've been spending a lot of time with that. Let's see, other questions we've got coming in here. What if that's a quantum problem? Well, actually, quantum computing would make a lot of this much faster because of how we could do the training. But yeah, that can be a quantum problem. Is any of the machine learning or Python going to be part of SEC 503? Guess what? It is already. In fact, I flew through this in just 90 minutes. We spend about between 4 and 5 hours building up toward building and manufacturing this right here, and how you do it and why you do it, and a couple of other useful machine learning approaches in 503. It happens in day 5. 503 was almost completely rewritten just this year. It just got released and on demand maybe 2 or 3 weeks ago. And day 5 is all, well, almost all data science and data analysis and useful stuff like this, instead of just being all theory. And let's see here. Yeah, solving across multiple global minimums. That is a great thing to do. There's research in that, but the problem is, how do you know how far to move? There are some solutions to that, Mary, and solution is a hard thing to say. One of the things that's used in it that I'll talk about for you because you brought this up is looking at the momentum. We can add some additional momentum and change the learning rate. I'm not manually adjusting the learning rates here in the gradient descent, which could help us if we have something that's falling down into maybe a local minimum that then rises and goes down to a global minimum. With that, by adjusting that learning rate manually, I can force it to kind of try to overcome humps so that it would fall to the deeper low. But if it turned out to not be going to a deeper low, it'll still settle back. I'm not doing that here. I just didn't want to make it too complicated. Thank you very much, Bogdan. Hey, it's good to see you. It's been a little while since I've seen you. Other materials and course lab or books on this? Yeah, there's a gentleman by the name of Francois Cholet, I think his last name is. Forgive me, I'm not super sure how to pronounce his last name, who is the developer of Keras. He has a very good introductory book. It is purely supervised learning, so know that going in. I've also heard quite good things about a Python book on that, but I don't want to misquote the title. So if you don't mind, if you reach out to SANS, info@sans.org, or to the moderator, have them redirect a message to me, and I'll be very happy to get you that book recommendation, because there are piles of books out there, and I've read a bunch, and many of them are just terrible. So let's see. Thank you. I'm glad you enjoyed the presentation. It looks like we've got no more questions. It is 10 o'clock. I have, oh, wait, another question. Hey, I got Francois' name correct. Thank you very much. Momentum optimizer. That is what I was talking about. It's not what I'm using. So yes, someone was asking, are you using the momentum optimizer? No, I'm not. I think I'm using a ReLU in all of these, but I'm not certain. I'd have to go back. Oh, actually, that's the activation. I think I'm using, I don't remember what I'm using. I think I'm actually just using stochastic gradient descent with ReLU. I think Adam was in the notebook. Adeline is asking me this, but I think in my actual one in production, I don't think I'm using Adam there. But I do need to call it quits. If you do have more questions, feel free to reach out to SANS. They can put you in contact with me. We will be publishing much of the material here in the Show Me the Packets repository, at least some of the notebooks there, probably not all of our training data, because that just gets to be a little bit too much. Otherwise, I do hope you enjoyed this. I'm sure SANS is going to send you an eval, because that's just what we do. If you have more questions, reach out to me by email. Otherwise, have a wonderful night, and please be safe. Don't do stupid things during this pandemic, and I hope that everyone you know and that is associated with you remain safe. Have a wonderful night.